Alright, and here we begin homework number 3, starting with a basic conceptual problem where we're asked to draw some motion graphs for an object in free fall. So, first situation is a ball is thrown straight up in the air and it lands above the point from which it was thrown. So our position graph, I'm going to start it down here at the origin at a position of 0. It's going to be slowing down while traveling up on the way up to its peak, which happens right here. And then on the way back down, it's going to be speeding up with a negative velocity. So we're maintaining that concave down, that negative acceleration the entire time. But we have a negative velocity now. The one thing we just have to watch out for is we don't return to the same point where we landed. So we're going to end up here above where we started. For the velocity graph, we can either base it off of the position graph we just drew, or we can just think about our situation in general. We're starting up here with a positive velocity, and initially we're slowing down because we have a negative acceleration. So I'm going to draw a downward sloping line going to 0, which corresponds to this point here. Those 2 points are the same. We're then going to continue through that x-axis. We just want to make sure, though, that we don't get back to the same velocity that we had initially because, again, we land above where we started. So I'm going to just mark a point here and just continue to that point. Okay, so something like that, clearly ending with less velocity than what we had at the beginning. For the next one, a ball is thrown straight up and it lands at the same height. So same basic idea here, all right, starting from the point of 0, we're going up, slowing down on the way up to our peak, which happens right here, and then accelerating in the negative direction with that negative acceleration. Now we are going all the way back to where we started. And for both of those position graphs, you obviously could shift them up or down. All right, where you start doesn't actually matter. You don't necessarily have to start at the origin. For the velocity graph, all right, same basic idea. We're going to start with some positive velocity. We are slowing down because we have that negative acceleration. In this case, though, we are going to continue back to the same magnitude of the velocity we had initially, right? So we started with 1, 2, 3 units in the positive direction, and we end with 1, 2, 3 units in the negative direction. So we do have that symmetry here because we're landing at the same height. Our final is the negative of our initial. So those are what those graphs should look like. Alright, for this one here, we have a ball thrown up in the air, and the first thing we want to do is we want to draw the velocity and acceleration vectors for each point. I'm going to start with acceleration. That's actually the easy one. I know that at every single point, this object is accelerating down at 9.8 meters per second squared. So I should have a bunch of arrows, all with the same length, showing that that acceleration is the same the entire time. For my velocity vectors, and those will not all be the same. Initially, we're traveling up, okay, at that first point. When we get to this next point here, we're still traveling up, but not quite as fast. So I'm going to draw a smaller vector. At the peak, my velocity is 0, and then I begin moving down. So here, my velocity is downward, and it actually should be the same length as this one. These two are at the same height, so their velocities are the same, just opposite in sign. And then when I return all the way down to the bottom here, that velocity is going down, and it should be the same length approximately as this one. Alright, let's talk about some concepts here that we also know. We already have that velocity is 0 at the peak, so that's one concept we know. We also know the time here at the peak is half the total time. Okay. When we return to where we started, down here, our displacement is 0. And our velocity is simply the negative of our initial velocity. Moving on to our next one here, we have a person jumping straight up in the air, and they reach a maximum height of h after being in the air for a time of t. So how long is the person in the air before landing back on the ground? I'm going to draw a quick sketch here of this flight. So we start on the ground, we go up to the peak at a time of t, and that is at a height of h, and then we return to the ground. So this is a symmetrical launch here, okay, And that means that the time here is simply double. So our total time in air would simply be 2t, twice as much as the time to go to the peak. For part B, we want to know at time t over 2, so half the time as we're rising up, is the height of the person greater than, less than, or equal to h over 2? Okay, and the answer here is going to be greater than. And there's a few ways of thinking about it. The easiest way, I think, is this. We know that as we are going up to our peak, we are slowing down. All right, here our velocity is 0 at the very top. So what I would say is, as the object rises to the peak, it's slowing down. That means that it's traveling faster during the first half of the time than it is during the second half. And then we want to link this back to the distance, so I'm then going to say, therefore, the distance traveled will be more than h over 2 during the first half of the time. All right, and there we have it. One last thing, at what time will the person be at the same height as they were at t over 2? Once again, I'm going to draw my picture here. Here's my time of t. Here, a little bit more than halfway, is my time of t over 2. And so we want to know when we return to that height, which would be right in here. So if I think about it, it's going to take a time of t to get to the peak, and then the time to fall back to this point is going to be the same as the time it took to rise from this point up to the peak. So we're going to have an additional, just in this section here, an additional t over 2. So our total time is going to be t plus t over 2, or 3/2 t, or 1.5 t, whatever you want to call it. Okay, but the key is that the time it took to go from the t over 2 to the peak is the same as the time it's going to take to go from the peak back down, all right, to that same height. All right, so we just take the time up to the peak, which is t, plus that extra t over 2, and we get 1.5 t as our final answer. Okay, so for this next one, we have one of our ratio style problems. So we start here with the car initially traveling at a speed v when it slams on the brakes and skids to a stop. The distance the car skids before stopping is d. So suppose that the initial velocity was 2v. In terms of d, how far will the car skid before coming to a stop? Well, what I'm going to do here is, since I have two situations, okay, I'm going to actually set up two charts. One for when my car's velocity was simply v, and one for when it was this 2v. Okay, so in the v case, it starts with the velocity of v, skids to a stop over a displacement of d, and we're coming to a stop, so my final velocity is 0. In the case of the second situation, we now start with the velocity of 2v. We're still skidding to a stop, so the final is still 0. We don't know delta x, that's what we're looking for, and that's what we have. This last line here, assume the car slows down at the same rate, that actually is a really important line, because what that tells us is that both of these accelerations are the same and they're both negative, right? It slows down, so that gives us a negative acceleration since our velocity is positive, and they slow down at the same rate, so they both have a value of a. So what I can do now is set up an equation. You notice I don't know time, I don't care about times, but I can set up an equation in each situation that does not involve time. So for this first one, I'm going to say vf squared equals vi squared plus 2a delta x. So 0 equals v squared plus 2 times negative a times d. And I'm ultimately solving here for d, so that's why I want to isolate. So I get that negative v squared equals negative 2ad, so d is going to be v squared over 2a. Moving down to my bottom equation, same idea. Vf squared equals vi squared plus 2a delta x. 0 once again. Now it's going to be 2v. And be careful because it's that entire quantity that's squared, not just the v. The 2 is squared as well. And so what that means is I get 0 equals 4v squared minus 2a delta x. Ultimately, we're looking for delta x here, right? And so I'm going to say 4v squared equals 2a delta x, which means that delta x is 4v squared over 2a. Now, some of you might be able to look at this and compare these two and see what the final answer is. If that's a little bit tricky for you, what I'm going to do is a technique that we talked about somewhat in class, and that is dividing equations. So I'm going to say delta x equals 4v squared over 2a, and d equals v squared over 2a. And I'm going to divide those two equations. So on the one side, I'm left with delta x over d. And on the other side, dividing by this v squared over 2a is really the same as multiplying by the reciprocal, 2a over v squared. So what I'm going to get on this other side is 4v squared over 2a times 2a over v squared. Well, the 2a's divide out, the v squareds divide out. What I'm left with is delta x over d equals 4, which means that delta x equals 4d. Okay, for this next one, we have a number of ratios set up here. We want to think about what is going to happen to an object thrown vertically up in the air if we triple its initial velocity. So what I'm going to do is I'm just going to look at the original situation, and then we can look at that tripled situation. So if we think about the original, object starts here, goes up to the peak, falls back down. We know, as always, our velocity is 0 at the peak. So we also know our displacement is 0 at the end. So what I'm going to do is I'm going to say my initial velocity here is v, and I'm going to once again consider going up to the peak. Also my time here is half the total. So if I'm going up to the peak, my final velocity is 0. My acceleration is negative 9.8, but since we have no other numbers in here, I'm just going to say negative g, although you could have used negative 9.8. So we want to find a number of things. The first is the total time in air for this situation. So what I'm going to do is I'm going to say Vf equals Vi plus At. Okay. So 0 equals V minus GT, which means that V equals GT. So my time in air, well, time to the peak, I should say, is V over G times 2 to get my total time in air, because remember it's symmetrical, that's half the total. I'm going to find that my total time in air is 2V over G. Okay, now if I go and triple this, okay, I'm going to get that Vf equals Vi plus At once again. So 0 equals 3V minus GT, which means that 3V equals GT, and my time here is 3V over G. That's the time to the peak though, so times 2 once again. And I get that my new time, I'm going to call it T prime. Okay, my new time is going to be 6VG. Right? So, how do the two times compare? That new time, T prime, is 3 times my original time T. We could do a ratio trick and divide, but I think a lot of these are going to be easy enough you can see on your own. Right? We have this VT here, or V over G here, V over G here. The only thing that differs is this is a 2, and this is 3 times as much because it's a 6. Some of you might also be able to look at this basic relationship here and see that v and t are directly proportional, and if you triple one, you triple the other. Okay, moving on to part B, the maximum height. So what we're going to look at here now is we want to find this, so we really don't care about time for this part, so I'm going to use this equation, vf squared equals vi squared plus 2a delta x. 0, I'm going to the peak once again, so 0 equals v squared, the initial velocity, plus 2 times negative g times delta x. So v squared equals 2g delta x, which means that my displacement, the maximum height, is going to be v squared over 2g. Now if we want to look at the situation where it has twice as much velocity, I'm going to start right here with 0 equals 3v squared, and really this is squared too, plus 2 times negative g times delta x prime, and that simply is coming from this equation, just changing this v to a 3v. And so I end up getting, when I multiply this out, 0 equals 9v squared plus negative 2g delta x, and we solve to get the delta x equals 9v squared over 2g. Once again, some of you might see that both of these contain that v squared over 2g. So x prime here, I forgot to add that, but x prime here is simply going to be 9 times what delta x was. Now if you were to use division to actually get to this point by combining this equation and this equation, that does work, or you can just see what that relationship is. Either one is acceptable. Okay, now the final velocity when the ball returns. Well, if we use our concepts, we actually already know that the v final is simply the negative of the initial, okay, because it returns down here to the same height. So I can say my final is going to be negative v. If I'm dealing with the situation where it's 3 times as much, my final is simply negative 3v, and this one is the easiest of all to figure out, that this v prime here, is what I'm going to call it, is 3 times v, right? The normal v final that we get. So that was for part C. For part D, actually a bit of a trick question because the acceleration is always g, that 9.8 meters per second squared, and it's going down, okay? Anytime it's in midair at the peak or otherwise, that is going to be our acceleration. So we should know that no matter what. So there you have the first part of this homework 3 here.